Hello everyone. Today we'll be talking about predicting building energy consumption using machine learning, investigation of short-term and long-term trends. Out of all sectors of smart cities, buildings are one of the most important part. Most of human life is spent in buildings, and at the same time, buildings are also responsible for one third of final energy use and almost one third of energy-related CO2 emissions. Thus, to have sustainable and resilient smart cities, it is very important to have smart buildings and smart energy systems. Building energy management is thus an important aspect for smart cities. Historically, energy management in building sector is usually done by conventional method, which includes a comprehensive and stringent process of creating energy simulation models and its validation, which is often time consuming. But with advent of modern computer technologies and especially machine learning technologies, it is possible to smartly manage energy in buildings with fewer data sources which are easily available. The case study for this project is the EV building, which is located in downtown campus of Concordia University. It's an institutional building which was constructed in 2016 and has a built area of almost 70,000 square meters.
In this project, we have three main objectives. The first objective is to identify the key meteorological parameters with a high correlation with building energy load. The second objective is to predict the hourly electricity demand of the EV building for the upcoming 24 hours. And the third objective is to predict the electricity demand of EV building under the future typical weather conditions at different time scales.
For objective 1, we want to identify the key meteorological parameters with high correlation with building energy load. So first, we would like to develop a correlation matrix that will help us identify the relationship between the attributes and building energy load. We also calculate the Pearson correlation coefficient that will help us determine the strength and direction of the relationship between the attributes and building energy load. We also select the meteorological parameters with the highest correlation coefficient with building energy load. And finally, we would like to check the independence between the selected meteorological parameters. That is, we want to avoid multi-collinearity issues in the model by ensuring that the selected meteorological parameters are independent of each other.
Objective 2 is about predicting the hourly electricity demand of the EV building in the next 24 hours. The first step is using the result of Objective 1 about identifying the non-correlated attributes and in addition removing the least significant attributes from the procedure by feature selection in step 2. The next step will be modeling the prediction algorithm. We use the regression model and based on the literature review and class material, multilinear regression is extensively used in numerical prediction. However, it is counted as a traditional statistical method. In addition, random forest and support vector regression show better performance in short-term prediction as building energy consumption is usually nonlinear. So in this step, we are using multilinear regression, random forest, and support vector regression. And the last step is evaluating the models in order to identify the most efficient one. We will check the coefficient of determination, root mean, square error, distribution of error, and the linearity of relationship.
Objective 3 is to identify the most effective machine learning method for predicting long-term building energy consumption at different timescales. The first step is to prepare the building energy and weather datasets into different temporal scales, including hourly, daily, and monthly. And then we will use three machine learning models, including SVR, RF, and AI model, to develop prediction models across different timescales. The machine learning models will be trained and tested using above datasets. And finally, we will evaluate and compare the performance of each method using various metrics such as MAE, RMSE, and R-square.
The first dataset that we looked at was EV building measured electricity use data. It has 7 attributes, and we looked at the correlation metrics between them. The second dataset that we looked at is meteorological weather data. It has 7 attributes, and we also looked at the correlation between the attributes.
Regarding initial findings, here are the EV building data for 2019. We can see clearly here some interesting ups and downs in certain periods throughout the whole year. This is what we are going to explore, identify its reasons, and its relationship with our objectives.
In this project, we're following CRISP DM process. So far, we understood the context and identified our objectives. Then we explore the datasets and prepare the data for our next steps, which are modeling, evaluation, and deployment.